Record. Okay. I know a number of y'all, most of y'all are in the capstone presentations right now, so you're probably watching this on the recording. So um, a few things we've been having. I've had several people approach me about final exam arrangements. I've been saying for a while now that our final exam is at Tuesday from 11 until 1 o'clock. And there, you may have some conflicts with that. And I would expect that you would have already made arrangements for that. But if not, if you are seeing conflicts, you need to contact me immediately. This is very late in the game for me to be able to make arrangements since I teach remotely and I have to make a lot of arrangements to make a final exam happen. So our exam, I know that there's always something different that goes on, right? But our exam, um, since our class time starts at 12:30, should be on Tuesday from 11 until 1. And I believe I'm reading this correctly. So just really making sure that everyone's aware of that. And if there are any conflicts, that you see me immediately about that. All right, and I have also updated the exam preview on Moodle. So please take a look at that. We'll go over this shortly today. And also, I want to point out that well, most of y'all are probably going to be watching this recording, so you already know that my video lectures are on my Zoom channel, my Manhattan College Zoom channel, and so yeah, that should cover things. And let's see if there's anything else I need to talk about. So let's look through this preview now, right? So I have just copied and pasted the same equations we used before. This is the Shannon's capacity theorem that we talk about that relates capacity and um, bits per second to the bandwidth, a log base 2 of 1 plus the signal over the noise, signal power over the noise power, right? And then we talk about bandwidth efficient modulation, where we can take k bits and encode those into m different symbols. And that's going to be related by this equation here, right? So if you have a quadrature AM type modulation, that M would be 4 then, right? +1, -1, plus J, minus J, scaled by the energy, of course, or the square root of the energy. But then, so that would be 4 different symbols for quadrature AM. And then that means that you can encode 2 bits per symbol, basically. And so 00 would correspond to one symbol, 01 to another symbol, 10 to another symbol, and 11 to yet another symbol. So that's 4 different symbols to send 2 bits. But we only have to send one symbol. We just have to choose which one of those 4. And so we're able to send 2 bits via one symbol. So, for example, if our bit rate is 100 kilobits per second, and we're using quadrature AM or K is equal to 2, then our symbol rate would be half of that, but we'd be communicating that same amount of information, right? So it would only take 50 kilosymbols per second to communicate 100 kilobits per second. So, the same relation applies to higher orders of modulation, whether that's 8 quam or 16 quam, 64, 128, PSK, any of these bandwidth efficient modulation schemes. And so, but the scaling factor changes by this log base 2 event. Let me close my door. My dog is barking. Okay, sorry about the dog. All right, then this equation talks about the relates the noise process, a thermal noise process. So we've got Boltzmann constant and T here and bandwidth and that type of thing, right? So then we talk about the uniform distribution. Here's the PDF, and the PDF helps us understand a probability of a value lying between a range when we're dealing with continuous random variables. If it's discrete random variables, then there can be a finite probability that a variable will take on a specific value, right? But in the case of continuous random variables, the probability that a random variable takes on a specific value is vanishingly small, right? Because we're dealing with continuous variables, real numbers, and you can always divide that smaller and smaller and smaller, right? So it approaches zero in the limit. So with continuous random variables, we tend to talk about finding the probability that the variable takes on a value that lies between a range, right? And also, whereas the distribution, so that's the we indicate the density or the PDF with this lowercase f, and the distribution with the uppercase f. And so we can think this through. This is the probability that x lies when x is less than a, the probability is going to be 0. And then there's a kind of a scaling value, this x minus a over this b minus a. So, right, the uniform distribution is going to be flat topped, but bounded to a certain range, right? A on the low side, B on the high side. So this would be the probability that x lies between these values, right? So, all right, and then the Gaussian distribution, of course, this is the one that we've done quite a bit of work with, and mostly because our thermal noise and our additive white Gaussian noise channels tends to follow a Gaussian distribution. And so then when we want to convert back and forth between this f, little f, the density function, and the distribution function, we can either integrate from minus infinity up to that particular x value that we're focused on, or and using a dummy variable in that integration, or we would differentiate the distribution function to get the density, right? So you'll see in a preview, I'm not going to ask you to do any of these things, but just as kind of a review, it's important for you to know. Now, what you do need to understand is how to use Q functions in these, and I might add just another little formula here, because this the Gaussian distribution, as we look at what is the probability of, let's say, a variable being greater than a certain limit or within the range of a certain limit or something like that, we integrate this, and that gives us a something that we ultimately relate as a Q function, and then we look up that in this Q function table. And we've done that a couple of times, so you need to be able to do that type of work there. So then we've talked about probability of events occurring. These are kind of your axioms, right? So what's a probability of any event occurring has to be equal to or greater than zero, right? That's kind of common sense, but it's one of those axioms, right? And so it's zero if the event is impossible for that event to happen. If an event is the probability of an event occurring that exists in this space, this event space, is equal to 1, right? So that's implying that something's going to happen, right? So if we've got a coin and we're flipping the coin, and this space consists of heads or tails, we know that the probability of one of those events happening is 1. It's certain that it's either going to be heads or tails, right? So we use this capital Omega symbol to represent the entire event space. So if we're drawing, rolling a dice, and it can, it's a 6-sided dice. So 1, 2, 3, 4, 5, 6. The probability of the dice landing on one of those sides is 1, right? It's certain to land on one of those sides. Then if the events are independent, statistically independent, then the union of those events is simply equal to the sum of those. Otherwise, we need to understand the more the conditional probabilities involved in these things, or this intersection here. So we do work with conditional probabilities as Bayes' theorem, kind of a simplified version of Bayes' theorem, and we use this in our maximal a priori receiver. And this is the idea that if you know the marginal probabilities, and you know the probability of B occurring if A has occurred, then we can kind of swap that around and calculate the probability of A occurring if we know that B occurs. Now, we need to know these marginal probabilities also, the probability of A and the probability of B. This delta F min is equal to 1 over 2t. That's the equation we used when we studied frequency shift keying, and it was the idea of how close can we squeeze the tones together that we're using to represent the different symbols that we're transmitting when we use FSK modulation, right? And so we can squeeze those the difference between those frequencies together until the point where they're orthogonal to each other, and that gives us this relationship, and that's related to how fast we're signaling, right? So if we want to send our symbols faster, then we're going to need to put them farther away, right? So remember, t is a period, and our rate we usually refer to as r, and that's going to be the reciprocal of your period. So in a periodic system, right? So if we want to send higher rate symbols, then we need to space them farther apart to be able to separate them out, right? So here's our maximum a priori probability receiver equation, and then we note that with that, we don't have to assume that symbols are equal probable. If they are, we're going to kind of tweak our decision boundaries according to this equation to the point where we're favoring the symbols that have higher probability, right? So if we know that the symbols are not equal probable, but we know those probabilities, then we can draw our decision boundaries to kind of account for the fact that, well, all things otherwise, if we had to guess, we're going to guess in favor of the symbol that has a higher probability, right? So that just helps us have a more accurate result. So these are some kind of statement of a decision boundary, D1, and like a binary antipodal type of relationship. D1 would be giving you the position of the threshold when your probabilities are not equal, right? So there's some skewing here associated with that. So our energy of a symbol, we integrate minus infinity to infinity of the amplitude squared over time, right? So that's just kind of basic definition of energy. Probably learned that in physics, but maybe not. Have talked about signal amplitudes and that type of thing, right? So let's see. Then here we have our probability of a bit error. This will be important for you to understand. You did some homework, and I think we did a test exam using this type of relationship here, right? And this D12 squared, the D12 is the distance between constellation points, right? Or distance between symbols. And so that's related to how well correlated they are, what their cross correlation is, right? So we could calculate that, assuming that we know the time dependence of these two different symbols and their energy. Then we could calculate that correlation. But recall that we talked about some special cases, right? So the binary antipodal type of signaling is where we would have one symbol that's, for example, at a 1 or square root of the energy or something like that on the x-axis. And then the other symbol would be the minus of that, right? So equally spaced from the origin on the x-axis, but in the opposite direction. That correlation coefficient would be -1, right? Because it's really kind of the same, but it has that opposite signal, polarity, opposite polarity, sorry. So same energies here, and if you did this kind of correlation type of calculation here, this time average, then you would find that that's going to cancel out with these energies, but produce a minus sign, right? So then you would have 1 minus a minus 1 would give you a 2 inside that parentheses. Now, we also looked at orthogonal signaling, where one symbol might be 1 and the other one might be J or minus J or something like that, right? And they're orthogonal, and by definition, then this cross-correlation coefficient would be 0, right? That's the definition of orthogonality. And we can run through that. If this is going to be 1 comma 0 and this is 0 comma J, then or however you want to note that, then you can run through this calculation and find that rho is equal to 0. But just remember that, right? That if it's quadrature, that rho is equal to 0. If it's antipodal, the rho is going to be minus 1. A row of 1 would mean that basically they're the same symbol, and that wouldn't be useful in communications because you can't send identical symbols and hope to distinguish those at the receiver, right? So we're trying to send distinct symbols so we can determine what is what at the receiver, right? So well, I think I'm probably going to need, I might need some more equations here. Maybe not. So this signal to noise ratio, this gamma, we can relate to the energy per bit to the noise here. And so then you could, let's say on your given gamma sub B, then you can relate the energy up here to gamma sub B and N naught. And then, with your knowledge of rho, then you can calculate D sub 1, 2 squared, plug that in up here. Your N naughts will end up canceling, and you'll end up with some factor in here. And then you look up that argument X here in the Q table, and that produces a Q, right? So I think we've done some problems where you looked up, I think on a test or homework, you were the result was X equals 4, and then you looked up this Q value, and that would give you that probability of error, probability of bit error. And we also did some work where we kind of went the opposite direction, where you were the problem gave you a Q value, and then you had to find the argument that produced that Q value, right? So and then this is a simplified version of BPSK. Remember, BPSK means binary phase shift keying, which is essentially 0 and pi as the phase of the angles, right? 0 or 180 degrees, or normally we talk in terms of radians, so it'd be 0 and pi. That's the same as binary antipodal signaling, right? Because if you plug pi into a cosine or maybe an exponential of a signal, e to the j omega t plus phi type of thing, then that produces a -1, right? Cosine of 0 is 1, cosine of pi is -1, right? So the binary phase shift keying gives you basically is the same thing as binary antipodal signaling, or you could put it in terms of quadrature AM also, except there's no quadrature component, right? It's just a +1 and a -1 type of signaling. So, all right, so that's just kind of refamiliarizing you with the equations we've generally covered. Obviously, we've looked at a lot more equations than that, but we haven't necessarily done a lot of homework assignments or seen those on tests before. So, and some aren't very conducive to doing in a 2-hour final. So, I think that's probably all the equations you'll need. I have written the exam, and this preview is going to help you focus your studies for the exam. I have not derived all the solutions yet, so hopefully there's no gotchas there. But as I go through and do the solutions, then if I see that, oh gosh, I forgot I needed this other formula, I'll just add it. So be aware that if I've forgotten a formula, hopefully I'll add it there and stuff. So and if it's a type of formula I think is confusing on how to use, I'll send out that as an announcement to try to clarify that. So the test as currently stands is 20 questions. A lot of those are 1 point, maybe 2 point multiple choice or short answer questions, right? So hopefully they're easy, but you should understand the material, right, to be able to get the correct answer. The downside to having multiple choice is it's hard to give partial credit. So if you miss it, boom, that's a point off your grade and off your final exam grade. Final exams were 25% of your final grade. So if you miss 4 points, that's 1 point off of your final grade. So the rest of the questions are going to be on the order of maybe 6, probably more like 10 to 15 points each. And they are involving computations, or you're going to be asked to sketch a constellation or two or something like that, right? Or sketch something. So then the computational questions are mostly from your homework or previous exam questions. You should know how to work with the Q function and Gaussian random variables, know how to sketch a constellation, and the significance of changing M or K in a bandwidth efficient modulation scheme. Right? Again, bandwidth efficiency, we mean that we're mapping multiple bits to a single symbol, right? But we need a large symbol set to account for all of those. But we only send one symbol at a time, but that is made up of a number of different bits, right? So if you and it's kind of easiest if you kind of picture or even sketch a constellation of that, right? So if you have let's say a constellation that's 16 symbols, then let's see, the log base 2 of 16, capital M would be 16 then, and log base 2 of that is 4, because 2 to the 4th is 16, right? So we'd be able to encode 4 bits into a single symbol. Now let's say we want to and so that's what we mean by bandwidth efficient, because if our bits are coming in at 100 kilobits per second and we're taking 4 of those bits to make up a symbol, then our symbol rate is going to be 1/4 of that, or 25 kilobits per second, right? So we're going to need less bandwidth in our channel to be able to send that, right? So if we do that, though, then if we keep our borders, the outside borders of our constellation constant, and basically is another way of saying that our maximum power or energy is the same, right? And if we increase the number of constellation points, then necessarily they've got to get squeezed together closer and closer, right? And that means that distance between the nearest neighboring constellation points is going to shrink, which means that if we have the same level of noise, then we're going to experience more errors, because it's going to be hard to distinguish which ideal constellation point is represents the symbol that we receive. Conversely, if we want to keep the same distance that would correspond to the same error rate, then we would need more power, more peak power to send a larger constellation if we wanted to keep that spacing the same, right? So that's an important relationship there. So know how to find decision boundaries, right? So these are your thresholds, trying to decide if we receive a symbol, it's going to be corrupted by noise and maybe other issues, other non-idealities. Then we want to a methodical way to map that to the ideal symbol that was sent, and then we can decode that into bits, right? That's what we're trying to do. And so we can draw decision boundaries, and if they're equal probable, that's kind of easy, right? We just kind of figure out how to split those boundaries up, and then we can also draw and label decision areas, right? So the areas would be in between those thresholds, of course, and the interior of a constellation. Those areas are probably bounded by thresholds associated with other nearest symbols. On the edges of a constellation, those areas run off to infinity, right? Either on the x-axis, on the or the real axis, or the imaginary axis, or both, right? So all right, and then be able to calculate probably an error for an equal probable binary signaling system, right? So if we go back to our equations, that's basically this guy here, right? So, all right. Understand the advantages of a raised cosine symbol, shape, or a filter, right? So we talked about raised cosine filters. The filter is really there to create a particular symbol shape in the time domain, and that's because when we send a symbol in a bandwidth limited channel, then there's going to be some convolution of the channel frequency response with the symbol itself, right? So if we send in like a square pulse into a band limited channel, then we're going to get a sine x over x type of shape, right? And assuming that band limited channel is an ideal rectangle, right? And in the frequency domain, which mean that it has a sine x over x shape in a time domain, a rectangular pulse in the time domain convolved with a sine x over x shape time in the frequency response of that channel is going to produce a sin x over x type of shape, symbol shape. And we saw that the nulls of that symbol would lie at the peaks of the other symbols, right? So that's kind of a recurring theme. We see that in the frequency domain in OFDM type modulation, but we see it in the time domain in this intersymbol interference issue in band limited channels. And so the if your timing is ideal, then yeah, there's no energy in these other subsequent symbols or preceding symbols because their nulls lie at the peak of the symbol that you're sampling at any given instant. But we don't have ideal sampling, and so the sin x over x shape is rather steep in that sampling region. So a raised cosine filter has a shallower shape around that ideal sampling point. And so we end up with less error energy in our sampling process. Okay. And that's because it's, being smeared from an ideal rectangle to some, sin over x over x, or in this case, a raised cosine type filter, type pulse response that's a little bit friendlier to sample when we have non-ideal sampling. All right. Then with linear block codes, be able to calculate a code word for a linear block code given an input message and a generator matrix or purity equations. Okay, so we had this at the last exam, or maybe the midterm, I don't know. And a lot of people got that kind of backwards, right? So you're multiplying the message vector on the left and the generator matrix on the right. You just do a standard matrix multiplication, and that should produce your code word, right? So just get that order straight. It's got to make sense in terms of that matrix multiplication dimensions. All right, I'm going to stop here and start the next Zoom session.